गुड आफ्टरनून सर।
हाँ, गुड आफ्टरनून डॉक्टर साहब, कैसे हो?
ठीक हूँ सर, आप ठीक हो सर?
बढ़िया है, सब ठीक है।
तो बस जस्ट
योगी
5 मिनट।
सर आप।
हाँ, तो ये जूम पे तो मैं पहली बार ही कर रहा हूँ।
अच्छा सर। हाँ जी।
हाँ, चलो खुल तो गया।
हाँ जी।
अब इसको स्क्रीन शेयर करना पड़ेगा, बस वो क्या?
हाँ जी, करवा देंगे स्क्रीन शेयर आपका जो है। हाँ जी।
ओके, इसमें नहीं दिख रहा है ग्रीन।
सर नमस्कार।
नमस्कार नमस्कार मैडम, कैसे हो?
सर बिल्कुल ठीक है।
एक बात है डॉक्टर साहब, एक चीज तो बढ़िया है, वैसे तो आना जाना रहता नहीं ऐसी
डॉक्टर
बात
साहब
है।
नहीं दिख रहे फोटो। आप
फोटो
घर
दिख
से कर
जाएगी।
रहे हैं, कॉलेज से कर रहे हैं?
सर कॉलेज में ही है सब लोग।
ओके।
अब आ गए होंगे देखो। कमर बंद कर दो। डॉक्टर साहब, डॉक्टर साहब, पार्टिसिपेंट की कोई कारण सर बोलेंगे वो बोलेंगे हम अपना म्यूट कर देंगे ताकि हमारी आवाज नहीं जाएगी। बहुत ज्यादा पर कोई बोलने के टाइम तो म्यूट करना पड़ेगा, कोई मजबूरी है, बाकी म्यूट रखेंगे तो कोई दिक्कत नहीं। वाइब्रेशन का तो है। हाँ जी। हम्म। बोलना पड़ेगा। कॉन्टेक्ट लेंस तो मेरे को पॉलीमर है। हाँ क्या है? हाँ हाँ हाँ, मतलब ऐसे पूछ सकते हैं। कई बार वो टीयर वगैरह भी हो जाता है ना बीच में आईज के, तो वो पूछ सकते हैं। विच पॉलीमर इज यूज्ड फॉर कंट्रोल ड्रग रिलीज। अरे ये तो वेबिनार है, ये मीटिंग नहीं है, ये तो इसमें तो वही वही बोलेंगे, मैंने क्या करना। तो होगी तो 1 बजे नहीं 12:30।
क्लोजिंग पैकेट अच्छा। Good afternoon to all of you. I am L. Garg, convener of webinar on behalf of DN College faculty and Department of Chemistry. Welcome you all. Welcome you all in this national webinar on polymer structures, properties, relations and applications. It is my great pleasure to introduce our webinar speaker for today, Dr. Zainul Dia. Dr. Zainul Dia received his PhD degree from Kurukshetra University, Kurukshetra in 1991. He joined Guru Jimeshwar University, Hisar in 1995 as assistant professor, where his research work was focused on flame retardant polymers and nanocomposites. Presently, he is Dean, Faculty of Sciences and Technology, Guru Jimeshwar University, Hisar. He has more than 50 research publications in national and international reputed journals. During 25 years of research work in the field of polymer chemistry, he has made fundamental contributions to polymer applications. Dr. Dia was awarded many international fellowships like DAD, Germany, Commonwealth Academic Staff Fellowship, University of Walton, Manchester, UK in 2011. Till now, 10 students completed their PhD and 8 are pursuing under his guidance. I also welcome Dr. Vikramji, Principal, DN College Hisar, and patron of this webinar. I welcome webinar coordinator, Dr. Sunita Lega, organizing secretary, Dr. Achna Malik, and various other organizing members. Welcome to all participants joining this webinar from different parts of states and country as well. The webinar aims to address the revolution in synthetic polymers. This is the topic in which we all are deeply interested because polymer has become integral part of our daily life activities. I hope you will learn a lot today. Now I request our worthy principal, Dr. Vikramji, to express his gratitude to our speaker, Dr. Vikramji.
Good afternoon, all. On the behalf of Dayanand College Hisar, I welcome our Honorable Chief Guest and today's resource person, Professor J.B. Dahiya, Dean Physical Sciences, Guru Jambeshwar University of Science and Technology. He is a very soft-spoken person and learned scholar. I am honored to announce that Professor Dahiya is alumni of this college. He passed BSc Non-Medical from Dayanand College Hisar. Sir, आपका अपने ही कॉलेज में स्वागत अभिनंदन है. Today, sir will enlighten us on the topic polymer structure, properties and application. Sir, now I invite you, please deliver the lecture. Am I audible?
Yes, sir. Yes, sir, you are audible, sir.
Hello. Hello.
Yes, sir, you are audible, sir. Please.
And screen is visible?
Yes, sir. Yes, sir.
Yes, sir. Screen is visible.
Okay. Thank you. Good morning to all. First of all, I would like to congratulate the principal, Dayanand College Nisar, Dr. Vikramjit Singh, for organizing the national webinar on the topic polymer structure, property relation and application. And also I would like to thank for giving me opportunity to interact with the colleague and students. I also would like to thank Dr. ML Gar, the convener of the seminar, and for speaking nice words about me. Also, I would like to thank all organizing committee members who arranged this webinar, Dr. Rachna Malik, Dr. Sunita Lega, and also all my colleagues who have joined and students who have joined this seminar. I would like to speak on the topic as already mentioned in the pamphlet, that the polymer structure, property, relation and applications. Some of you might have joined some refresher course, another lecture where I also deliver some part of this lecture. So please bear with me. So I think how
सर आपका शायद म्यूट हो गया है, एक बार चेक कर लीजिए प्लीज. हेलो. दया सर, आपका आवाज नहीं आ रही है.
हेलो, am I audible?
यस सर. यस सर, प्लीज.
सर का थोड़ा टेक्निकल इशू आ गया है, वो ज्वाइन कर रहे हैं 2 मिनट में
इट्स
दोबारा.
हाँ, इट्स ओके. इट्स ओके सर, प्लीज कंटिन्यू सर.
ज्वाइन कर रहे हैं दोबारा, जल्दी ज्वाइन कर रहे हैं.
हाँ जी.
सर की रिक्वेस्ट आएगी दोबारा से, आप ज्वाइन करवा देना. हेलो, am I audible?
जी सर.
सर की भी रिक्वेस्ट आ रही है, आप ज्वाइन करो.
Sorry for interruption. Our guest speaker is just joining us because there is some technical problems. Please wait for a few minutes. Sorry for inconvenience. There is a technical problem. Sorry for. Our honorable speaker, Dr. Jayant Gandhi, is just joining us because there is some technical problem or maybe due to light problems there. Sorry for inconvenience. In a few seconds, the problem will be resolved. Please bear with us.
डॉक्टर साहब आवाज आ रही है? हेलो
हेलो हेलो,
आवाज आ रही है डॉक्टर साहब?
बिल्कुल बिल्कुल आ रही है।
ओके। उसके पावर जाने से सब, फिर इंटरनेट भी चला गया और सब चला गया, फिर लैपटॉप का अरेंज किया।
ओके ओके,
तो
नाउ प्लीज कंटिन्यू नाउ।
डॉक्टर साहब स्क्रीन दिख रहा है, विजिबल?
Visible, sir.
ओके, थैंक यू। सॉरी फॉर डिस्टरबेंस।
It's okay, sir. No problem.
Okay, so we all know that the polymers are very, play important role for human life, and we all know. And disturbing. Just wait. Yes. So all natural polymer, for example, cotton, wood, rubber, wool, leather, silk. So they are serving the humankind for many centuries. And we all know in the present situation, in today's situation, under the COVID-19 pandemic, the personal protective equipment role, we all know that they are protecting against the infection. And infection material for the health workers and playing a great role. So these polymers used in the form of the gowns, gloves, shield, overalls, they are used. And now we are not talking about how they will be, I think they will be disposed of, etc., because they are so useful. So now everybody knows without the these protecting these fabrics and or gloves type, it was difficult to prevent the transmission of the COVID. Na? So it's so important. And we know that the polymers generally they are organic compounds and their properties are related to their constituent structural elements and their arrangements. Although the polymers have many drawbacks than the traditional materials, there are such as they have low strength and they have temperature limitation in service, particularly their tensile strength is low, particularly for thermoplastics. So they also creep. Creep means they show the time dependent properties, but they also possess advantages, many advantages. That's why their total volume consumption are increased than the other known material, for example, steel, as they are readily moldable, they are resistant to corrosion, and they are electrical insulator, thermal insulator. So nowadays, we can also modify the modify to the and develop the conducting polymer also. So and also the most important property, the inflexibility of the polymers is very important. So that's why we have the rubber in use. And although their modulus and the strength, absolute strength and modulus is very low, but their specific value per unit weight or per unit volume are very favorable. So they have application in aerospace industry also. So they are different than the simple molecule in the way that they don't have the absolute molecular weight, exact molecular weight. So polymer are characterized by the molecular weight distribution because they have different chain length and different grades and different molecular weight of the same polymer. And they have the different size. So their molecular weight are measured as averages, number average molecular weight average molecular weight, etc. And we also, if we take ratio of weight average molecular weight and number average molecular weight of the many polymers, then which is known as the dispersivity. So from there we can see that how their molecular weight are spread. So if this ratio, the weight average molecular weight and number average molecular weight of a polymer is around unity, so that we call them the monodisperse polymer, which are rarely occurs. So most of the polymers are not monodisperse. They have the value more than 2, and their molecular weight also we can determine. We have many methods. The most simplest method is the viscosity method. So relative molecular weight we can determine using the Markov equation, the simple expression using the viscometer. And industrially, the polymer we can classify mainly two classes: plastics and elastomer. And plastics can be further classified into thermoplastics and thermostatic polymers. So we can add also here another class, that is the fiber. Some plastics acts as fiber also. So these are the mainly the classification if you want to start their classification. So basically there are two types of main polymers, the plastics, thermoplastics and thermosets. Greg sir, am I audible? It is okay?
Yes, sir.
Okay.
Audible, sir.
So I have taken a table where we can understand the difference, some important difference about these two type of the polymers and thermoplastics and thermosets. So thermoplastics, they become soft when heated, and when we cool them again they become hard. So we can process them again and again. So we call them reversible, and we can say the repeatable. And generally we can fabricate the many objects and items and products by heat and pressure of the thermoplastics. For example, the example are nylons, polymeryl chloride, polyethylene, polypropylene, polystyrene. These are the common plastics which are used. So they have the important one more factor, that they have these secondary bonds which can be reduced after increasing the temperature. So they have the plasticity, and the important point is we can increase their plasticity by increasing the temperature, and by varying the temperature we can accommodate their plasticity. So they are recyclable. In case of thermosets are very strong, and they also require heat and pressure to be molded, to be set in a particular shape. But their setting takes place because of the chemical reactions, and cross linking takes place there. So curing agents are added here. Sometimes the curing takes place on their own at a particular temperature. So thermosets, they are different in thermoplastics, that they cannot be recycled. We cannot recycle them again and again. Once they are set, then they are set. If we heat them, only they will degrade. So they have advantages also, because they form the strongly cross-linked structure, three-dimensional network structure. So they are strong, although they are brittle than the thermoplastics. And most important advantage is there, that they have dimensional stability. They don't change their dimensions when they are in use, when they are under load. So they are resistant to creep. So they can be used to a long time without changing their shape and their form. So for example, initially the cross-linking thermostats resin, for example, bakelite, it was used starting from in 19th second half of the 19th century. And epoxy, for example, rhodite, we use in our homes, that is cured with the curing agents, amines. And common examples of the thermostats are phenolics, epoxies, and unsaturated polyester and amino resins. These are the common examples. So origins of the polymers are the sedimentary geological deposits from they are the origin of the crude oil, or which are the origin of the synthetic polymers. So they are formed from the marine organisms. And the largest known reserve we know all are in Middle East, and most of oil extracted, which is used as a fuel. Only small percent of uh, this goes to the chemical routes, So the crude oil generally is distilled to separate the fractions, and industry requires predominantly the fractions from carbon 1 to 5, and which is obtained by distillation They are cracked into steam using the thermal and catalytic cracking. So refinery, we have the refinery at Panipat where this process also occurs. And the chemical aspect of the polymers, formation of polymer that we know, that is known as the polymerization. Polymerization is a process where monomers are as a repeating unit are added and they form a polymer. So this process we call the polymerization. So initially, the scientist, the W.S. Carothers, who gave the classification of the polymerization based on the two-step growth polymerization, that is condensation polymerization, and another is the addition polymerization. But later, the P.J. Flory, the scientist, polymer scientist, who got also Nobel Prize, I think in around 1953, 50, around 53, he also classified based on the mechanism which is more appropriate. In the major, there are two major classification: addition polymerization or the chain polymerization. Here, the addition polymerization, the unsaturated monomer units are attached in a chain. For example, acrylonitrile. So here, double bond is responsible for uh, addition of the monomers and forming of a polymer. So see an example of polyacrylonitrile and polymeryl chloride. And they have the three steps of formation. Generally, the initiation, first step, then propagation, then termination. And initiation is done using the common initiator. The benzyl peroxide is generally used as a initiator. And in the earlier days, the polypropylene was synthesized at the high temperature and pressure. That was the old method. And the polypropylene form was the atactic form. Atactic form, and which was soft and was not, we were not having so many application of polypropylene. But after the advent of Ziegler-Natta catalyst, Ziegler-Natta, these are the two scientists, both have got the Nobel Prizes in 63, 1963 and 65. So they have, because of this advent of the catalyst, because of Ziegler and Natta, because of the coordination polymerization, we were able to produce stereoregular polymers. Okay? Because of this, we were able to produce the polymer at low temperature and pressure and using the catalyst. So for example, the polypropylene, now we can synthesize very easily the isotactic polypropylene, which has a particular regular symmetry, and using the Ziegler-Natta catalyst, and it has so many advantages. Crystallinity is increased of this polymer, and so it has so many extra properties. So in addition, polymerization, the polymer, for example, polyethylene, polypropylene, polyvinyl chloride, polystyrene, polytetrafluoroethylene, these polymers can be synthesized. Other is the step growth, or we can say condensation polymerization, where two monomer attached with each other and small molecule is eliminated, such as water. For example, the formation of polyester, the polyethylene terephthalate, which is we use as in a fiber form, and also the bottles also are made up of the plastic, the good one bottles from the PET, and the fiber we know the fabric, the terylene. This is of the polyethylene terephthalate. So this is synthesized by the polymerization process of the condensation polymerization. So a reaction is shown here. Now, their structure and the property, that is the part which is also very important. So the properties of the polymer, the changes in a predictable way as we proceed from the gaseous material through the liquids to the wax. So as we progress to continue to the, for example, polyethylene, so up to 100 carbon atom, the wax, it is a wax, but the polyethylene more than 1000 carbon atoms, so it would have been very hard. The way the gas, then the liquid, and then the wax within 100 carbon atom. If we have the polymer more than 1000 carbon atoms, then it would have been very hard. But we find that polyethylene still it is soft, flexible, and its modulus strength is also very low. And the reason is that the chains, the polymer chains, which are convoluted into the balls, and so they are arranged in the random walk type arrangements. And polymer mechanical response not only depend on the chemical bond, but also the secondary bonds, for example, van der Waals forces. So before we understand their property, so there are two states of the polymer which are important. Generally, the polymers have found in two states or containing both the state. For example, crystalline polymers. In crystalline polymer, we all know what are the crystalline, what is the crystallinity. So in crystalline polymers, the chains are in order up to a long range, and there for crystalline polymer we observe the melting point, a sharp melting point, not in a small range of melting point. And there are some polymers which are amorphous. So we say in amorphous the chains are not arranged in order up to a long range order. So here they don't give the melting point, rather the important property, that is the glass and temperature, is measured in that case, that is the Tg. So this is the melting point, this is the glass temperature. So we have the polymers are not 100% crystalline, neither 100% amorphous. They possess both the state. So we call them, there are most of the polymer are semi-crystalline polymers. So semi-crystalline polymers show both glass temperature and melting point. So generally the polymers having more than 50% crystallinity, we call the crystalline polymer, and less than that the amorphous polymers. So the crystalline polymer, they possess the crystalline polymer. We all know they possess latent heat of melting. They absorb the certain heat, that we latent heat of melting, and undergo a change in the heat capacity. When heat them, temperature is increased. So this way we obtain this type of the graph. So any change brought about heat, which has a change in heat capacity, where latent heat is involved, is thermodynamically we call them first order transitions. And the amorphous polymer, where we observe the glass and temperature, see this is the case. When heat them, temperature is increased, and this is how the temperature increases, we can see here. So the temperature does not stop because they don't have any latent heat. So in case of crystalline, we are giving the heat, but temperature is not changing for a while. So this is a melting point. So in case of amorphous, the temperature does not stop, it continuously increases. So this is the second order transition. So this is the basic difference we should I think remember. See this is the another schematic diagram where we have shown the DSC, differential scanning calorimetry, of the polyethylene and the polymethyl methacrylate. So polymethyl methacrylate, this is the amorphous one, and polyethylene, it may be the crystalline or semi-crystalline. So in case of crystalline, when we take the DSC, so it shows the clear-cut melting point. See here, this is the melting point. And we also, when we cool it, when crystallize, also it gives the exotherm in the reverse phenomena. In case of amorphous, we don't see any peak, no exotherm, no endotherm, just we see the deviation in case of amorphous when we take differential scanning calorimetry measurement. So see the semi-crystalline, this is the figure in case of semi-crystalline. So these are the crystalline region, and in between these are the amorphous region. And see the amorphous one, this complete random one. So these are the pictures we observe. We explain by these, the semi-crystalline and amorphous. And we take the, generally we do the analysis by XRD. So when we take the XRD of the polymer to know whether this is the amorphous or this is a crystalline polymer. So X-ray scattering produces diffuse holes on the photographic plate. So this is the diffuse holes for amorphous polymer, and the ring, sharply defined ring, in case of polycrystalline samples. So this is the first difference we can see. Okay, the polymer is crystalline or the amorphous. And when take the spectra of XRD spectra, also we obtain the counts versus the 2 theta angle. So there, in case of crystalline, the different planes, they have the different sharp peaks. In case of polymers, we have only the broad peaks against the 2 theta angle in the XRD. So there is a mechanism for crystallization. We will discuss more of the crystalline state and amorphous state. These are the important states of the polymer. Because of that, they have the different properties. So the mechanism of crystallization, we can explain whether they will crystallize or not, why they are crystalline, why they are not crystalline, because of the two factor, the two way, thermodynamic and kinetic. So thermodynamically, if we this is the thermodynamic expression, G is equal to H minus Ts. When polymer is melt, so when polymer in the melt form, so we will say that it will attain a state of maximum entropy, consistent with a stable state of minimum free energy. And crystallization, we know, is a process involving orderly arrangement of the chain and is associated with the large negative entropy activation. So a favorable change in gives free energy is to be obtained for crystalline formation. It should be negative. So greater the intermolecular forces between chain, more favorable will be the energy, this H1. So that's why it will become the negative. So from here we can have the indication that which polymer chain will crystallize. For example, the two indication, the symmetrical chain, which allow regular close packing, which is essential for the formation of the crystallites. The chain possessing groups which increase the strong intermolecular interaction, also they also stabilize the alignment and they crystallizes. There is also another factor other than the thermodynamic factor, that is the kinetic factor, that is related to the flexibility and the mobility of the chain. That should also taken into consideration. Okay? So the restriction of crystallization generally is in the range of the temperature between glass and temperature melting point. So everything happens between these temperature, glass temperature of polymer and the melting point of a polymer. So there are two steps we will take for consider two steps for mechanism of in case of understanding mechanism of crystallization. First step is formation of the stable nucleus, and then the other chain will brought to that in parallel array in ordered way using the intermolecular forces. So stabilization takes place up to a long range in three-dimensional order. Second step is then growth of that. So growth of that, the other chain will come and will add to the nucleus. So there the temperature had its role. So generally the optimum temperature for crystallization that occurs generally between 10 degrees centigrade less than the melting point and 30 degrees centigrade higher than the glass temperature. So this we have narrowed the temperature where we see the crystallization occurring in this range. So formation of crystalline stable region, so we require the economical close pact of chains in 3 dimension and favorable change in internal energy during the process. So we also see some the factors which affect the crystallinity and of course the melting point also. So these, what are the factors we affect? This is the symmetry, intermolecular bonding, tracticity, branching, and molar mass. Let us take the simple example. In case of symmetry, let us polyethylene and polytetrafluoroethylene. These are considered, these are the symmetrical one, and we consider them a smooth cylindrical rod. So these are the rod with roll, we tend to roll over each other and change their position when thermally agitated initially. So this is called pre-melting. So most of the polymer processing, so that's why pre-melting is important. Before processing, we heat little bit for some time, then we process them in the processing machine. So what happens in the pre-melting, which increase the entropy of the crystal and effectively stabilizes it. So more thermal energy is needed because crystal becomes unstable. So the melting point is increased. More symmetry, more packing, so more crystallinity, so more heat is required, so melting point increases. So we have some example. For example, these are the three examples. The cis double bond, orthometa phenyl group, cis oriented puckered ring, they all increase the bending and twisting of the chains. They don't allow the setting the chain in a closed packing, so there is difficulty. So so that's why they are less crystalline there, and their melting point will be low. Okay, so on the other hand, the poly oriented para oriented phenylene rings, they retain the axial symmetry and they crystallize more readily. And also we can compare the cis and trans. We can see this poly 1,3-butadiene and trans poly 1,3-butadiene. Lot of difference in melting point. In this case, in the case of cis, this is 262, and in case of trans, this is 421. So trans, the geometry that the close packing takes place, they are more stable in case of the trans. So intermolecular bonding also plays a great role. So close packing allows the van der Waals forces to act cooperatively, and they provide the additional stability to the crystalline. So strong attraction is there because of the either hydrogen bonding or dipole-dipole interaction. For example, you see the case of nylon 6,6. So there is hydrogen bonding, so it has high melting point, and polyethylene there is no. This is polar attraction or hydrogen bonding, so its melting point is very low. Tacticity, the isotactic polymers, they form the helix. Helix, for example, polypropylene, it forms the 3-1 helix. The helix means they are stabilized. They take a conformation, a such conformation, which is more stable, and their packing is better. So they become stabilized. So take the example of polystyrene. When it is atactic, it is amorphous. When it is isotactic, this is the semicrystalline. So in case of isotactic conformation configuration, it forms the helix. So close packing, so crystallinity increases. Otherwise, atactic means the random symmetry. So in case the amorphous polymer is present. Branching also affect the, if chain is branched, so packing efficiently decreased and crystal contact is lower. Okay. For example, the branching in side groups that stiffen the chain, and it stiffens, so it raises the melting point also. So molar mass also affect the crystallinity, and the molar mass means the length of the chain, or its length of the chain or molecular weight, how it affect the crystallinity and melting point. Because if we have the low molecular weight, means we have the smaller chain length, it means we have so many ends in the material, in the polymer moiety. So chain ends are relatively free now to move. So many ends are there. So they are free to move. So number of chain ends increase, reducing the molar mass. So melting point is lower. You take an example of the polypropylene of the grade of molecular weight 2000. It has melting point 378 Kelvin, and if we increase, it is 30,000, then it reached the melting point increase up to the 443. So polymers of the same kind of polymer of the different molecular weight, they have the different melting points. So we must know all that, and similarly the crystallinity also changes. So another state, that is the amorphous state. So amorphous state, the important concept we must remember in case of amorphous state, that is the molecular motion. Only we always remember when we call the amorphous state, so we must always point to the molecular motion, and depends upon the molecular motion, and which molecular motion depends upon the flexibility and the temperature. So the complete understanding, we can understand amorphous state by having a mechanical behavior, or by having the measuring the modulus with the increase of temperature using the tensile strength tester. So see, this is the modulus, and this is the temperature increase. So here we can have a second graph. So this is the case example of taken of polystyrene, the atactic one, which is completely amorphous. So this is the best graph. So we have taken this shown here. So it is not necessary all the polymers will show this type of curve. Some this less, some this more, or some this less, some this more. Depends upon how much amorphous and crystallinity is there in the polymer. So molecular motions are considered to explain the amorphous state. See, when we take this, the modulus, we measure the modulus with respect to the temperature. When we heat the sample and we measure the modulus, so we see the 5 states generally. Here, this is the glassy state. We have classified into 5 states. The curve, modulus, this is the change of modulus. This is the increased temperature. So this is the glassy state, then leathery state, then rubber state, rubber flow, and the viscous state. These are the 5 states. And the temperature, this is the temperature, we call it glass temperature. It occurs here, where the modulus changes rapidly, drop rapidly. So somewhere here, this is the glass temperature. So this is the important temperature around which many physical property changes. So these are I will not discuss in detail different states. So with the increase from the glass to the leathery, motion increases, then more, then more, then more. So with the increase of temperature, their motions here are frozen, here are released, then increase, then more increase, then it becomes the viscous. So generally we process all the polymers in the processing machines. So viscoelastic state is the state where the polymer melts are present. That is the viscoelastic state. So here the two laws comes in between, the Hooke's law and Newton's law. The Hooke's law, it is applied to the elastic solids, where when we apply the stress, to the material. So stress here, according to the Hooke's law, is proportional to the resultant strain, and it is independent of the rate of strain. This is the Hooke's law. In case of Newton law, when it becomes melt and we apply the stress, so here when stress is proportional to the rate of strain, not the strain, rate of strain. So these are the two laws. We call them limiting law. In case of polymers, both laws are not completely applicable. So both are not describe the behavior of the polymer melt completely, and that is we call the state of the polymer viscoelastic state. So that's why the polymers we call non-Newtonian, not Newtonian, because they don't follow the Newton's law. They are non-Newtonian. They behave differently. So to understand the viscoelastic state is very important in case of the polymer. So viscoelastic state we can understand by taking example of the silicon polymer, which we also sometimes call the bouncing putty. So if we take the sample of it and we roll into a sphere, and it will bounce like a ball by rapidly applying the stress. Okay, when we apply the stress rapidly, so it behaves like a ball. But instead of that, when apply the stress slowly, then it will not bounce, it will deform. So material will flow like the viscous liquid. So viscoelastic state is the totally different. How load and stress is applied, then behavior is different. So we must know how the polymer in this state behaves. And the chain length, again, molecular weight, that affects the property, because the molecular weight, the different polymer have the different grade, different molecular weight, so it's important. So the effect of chain length, we can understand it by measuring the viscosity. This is the viscosity, we can by measuring it. This is called the zero shear viscosity. Zero shear viscosity means this much shear at the shear where it follows the Newton's law. The viscosity where it follows the Newton law, so that is the shear zero shear rate viscosity. So see this curve, this scheme, this graph, where we can see the effect of chain length, molecular weight, and many things we can see. This is important graph where the viscosity is plotted against the chain length. So Z is the chain length, this is viscosity. When you measure the viscosity of the different polymers having the different chain length, so we obtain this kind of the two straight line, this and this. So this plot have two linear portions, this one and this one, lower one and upper one. So here is a point, intersection point. So Z critical, ZC. Okay, above and below the ZC. So above this ZC, so this flow behavior of the viscoelastic polymer is explained by this expression, log eta 3.4 log Z. So here this is the slope 3.4. So above this point, here slope is 3.4, where the chain length are higher than a particular length. And below this point, the critical point of chain length, this equation is followed, where the slope is the 1. Here slope is 1, here is slope is 3.4. So this is the dividing point. So the chains below this point, they are too short, they have no significant contribution to the viscosity from the entanglement effects, we must know it. And above this point, chain are too large enough that they retard the flow. So only main effect takes place around here, in this value, around here. So Z is defined as the number of atoms in the backbone of the chain of the polymer. For example, in case of polyisobutyric, so this critical value of chain length is 610. So around 610 is viscosity is more affected by the other conditions. In case of polystyrene is 370, polymethyl methacrylate 208. So this is the characteristic property. So critical chain length is a characteristic property, and if we know that, so we can have idea how the polymer will behave under the stress. Stress means generally the polymers are melted in the machines and they are deformed. So how they behave there, so that's important. The mechanism is important. Flow mechanism is important. So there it helps. What is the viscosity? How viscosity changes with the condition. So that is very important point there. So there are two parameters, melting point and glass and temperature. Again, I am showing these two figures. So the important point is this is the glass and temperature. For example, generally we add the plasticizer in the plastics in the polymer to decrease the glass and temperature. Glass temperature decrease means we want to increase the free volume so that motion is there, so that they can slide over each other. Generally we see in the new cars, the dashboard, etc., that smells. So that because of the plasticizer present there. So plasticizer is added there so that glass temperature does not increase. It doesn't become brittle. If all plasticizer is evaporated with the time, then dashboard will become brittle. So plasticizer are added to have the appropriate value of the glass and temperature. For example, phthalate ester, they are added there. So glass temperature is very important. Okay, so the molecular motions, those are the important before the teaching, after the teaching. The molecular motions are there, but they are frozen below that glass temperature. Above the glass temperature, toward the rubber is straight, the molecular motions are allowed. So only it doesn't mean there are no motion. They have ability, but they are frozen, like they have hold their own potential energy like a strong spring hold. When we use it many times, it becomes loose, means now it doesn't hold the potential energy. So their motions, they are there in the frozen type. Okay, all the energy they have absorbed as a potential energy. So that's the important case. For example, you take the case of polyisoprene. Take the rubber, that is the polyisoprene, that is the natural rubber. So it is flexible chain, and this is the room temperature 300 Kelvin. So it behaves as rubber because the chain of that polyisoprene can have many conformations, 1,000 conformation within a second. So it's so flexible at the room temperature. And its ground temperature is around minus 70, 80, around 100 degrees centigrade of rubber. So at room temperature, polyisoprene, it behaves as rubber because the chain can have so many conformation at the room temperature within a second. So it behaves as a rubber. So it's elastomer, good elastomer. See, on the other hand, see the polymethyl methacrylate at room temperature, it is a solid. But when heat is polymethyl methacrylate, we take it up to 450 Kelvin, means about 150, 60 degrees centigrade. Now it becomes rubber-like. It behaves rubber. So confirm their motions of the chains are allowed, and it behaves like the rubber. So the polyisoprene and polymethyl methacrylate at room temperature, polymethyl methacrylate, this is the transparent one, the glassy one. It behaves like that. If we increase the temperature, rubber will behave as a rubber. The polyisoprene will behave as a rubber, but polymethyl methacrylate will behave as a elastomer. So now it cannot bear the load at the temperature more than 100. So that's why we cannot use it under the bonnet or somewhere the temperature is increased. So we must know polymer is how it behave under load at what temperature. So this is the basics is the what are the chain arrangements, how much flexible is that, what is the glass temperature or that. So that's why these all parameters essential to be known. So generally glass and temperature, you see most of the properties, for example, the specific volume, the modulus, the heat capacity, refractive index, and many other physical properties, they also changes at that glass and temperature abruptly. So they are different below and above the TG. So for example, you measure the volume or the enthalpy or the entropy when you increase the temperature. So this kind of the curve you will find. And in case of crystalline one, in case of amorphous, you see the continuous increase. So from when we extend these two linear portions, then intersection we can have, and from there the last temperature we will measure. So generally we take the first derivative of these. So we can of derivative of the H. So heat capacity we can see, and heat capacity changes, and heat capacity we can measure from DSC, differential scanning calorimetry. Similarly here, so this we can measure in the differential scanning calorimetry. We have the endotherm in case of melting point, and here is deviation in case of glass temperature. So I will now discuss the method of determination of glass temperature, because I will be moved. There are also many factors which affect the glass temperature. For example, the chain flexibility. See this table, how the TG affect. So what are the factors generally responsible for change in glass temperature? These are the chain flexibility, the steric effect, the molar mass, branching, and cross-linking. See this table here, and these are the TG, the last column. These are the repeating units. So generally, the chains, the polymer containing these simple chain, they are easy to rotate, so they have the low TG. As we add the aromatic ring are added to there, so their TG increases. So difficult to rotate. So this is an example that with the increase of the hindrance in the backbone of the chain, so rotation is not easy. So the movement is not easy. So we have to give more energy to make the motion, means to make flexible. So TG is increasing. So this is the one table where we can see. This is the another table. Is it visible? Dr. Garg, visible है table? Garg साहब?
Sir, visible है sir.
Okay. See,
Ji, sir.
See here, this is the another. So this type of the polymer, see, this is the, for example, X. So X changes, X group. Sorry. So this is the group X in this type of polyethylene, polypropylene, polybutene, pentene, hexene, then 4-methyl, then alcohol, then polar one, vinyl alcohol, vinyl chloride. See the act value of X. So the molar volume increases. TG is also increases. With the increase of the hindrance with this group increase. Then you can see the polarity comes in between. So here they becomes polar. Okay, so secondary forces come in between. So then TG is increase higher. It becomes more. So more polar, more the TG in this way. Then this is the group. See here, polymethyl methacrylate. Then methyl group, then ethyl, then propyl, then butyl. So here also this way this molar volume increases. So TG also increases. Here you can see this type of the polymer. Okay, X and Y, they are the two group. Methyl methacrylate, ethyl methyl methacrylate, propyl methacrylate, this way. So with the increase of this, the TG is also increases. Here see in case of polybutadiene, you see the cis and trans. Cis, that glass temperature is 165. The same polybutadiene, this is 255. Because this is more stabilized. This is the trans one, more symmetrical. So close packing, more crystalline. So it increases. So molecular motion freezes because it is stabilized. So we have to give more thermal energy, more heat to raise its motion. So TG is higher. Similarly, polyisoprene, cis and trans, there is a difference is here. And cross-linking increase the density, increase decrease the molecular motion, so it is increase the Gaussian temperature. So creep is very important. What is the meaning of creep? It is related to dimension stability. So polymer material must retain the shape when we subject under tension or compression. So polymer dimension stability is very important. So thermosets, for example, epoxy, they are set by cross-linking. So they don't creep. For example, plastic telephone receiver that sags after sitting on a cradle for several weeks, no use. Car tires that develop flat spots if parked in one position, that is no use. If we use the clothes made of synthetic fiber becomes baggy after a short period of wear, there is no use. So dimension stability should be there, which the fibers have. So we must know what is the dimension stability, what is the creep behavior of a polymer. So we must know, only then we can use the fiber and those have the application. So creep test generally we do, that is the tendency to deform. Here is a another this diagram. When stress is applied, then how the strain takes place. This is the first, then this is the rapid response. This is the creep, air creep take place, and then this is the plasticity and the elongation here. Then stress is removed. Then how it comes back in similar way or different way. In case of elastomer, the E dash, this one equal to this one equal to this. If it is less plasticity, less elastomer, then these values are different. So this is the another way to, this is the creep curve, and we can have many understanding of this is the stress strain measurement, this is the break elongation, whether is the polymer will fracture or not. So this is the tensile strength tester curve. So this way we obtain this curve. In case of brittle, they will break here. So how much energy required under that this curve, we can measure the energy required. If it is elastomer, there will be yield point, and like this curve is obtained, it will break here. So more energy required to break, so long elongation. So generally fiber behave like this and elastomers behave like this. Okay. Now let's generalize that structure property relations, how they are important. Increasing use of synthetic polymers by industrialists and engineers to replace and supplement more traditional material. So we need a search for a versatile polymer structure covering wide range of property. Okay, so we must know the fundamental knowledge of structure property relation. Only we know the structure, what is the structure, what is the property will become. Only then we can develop and we can search the required material, polymeric material. So in the broad way, again, the two way we can look the polymer. If we want to develop, modify and a polymer, our required with our required property. So the chemical way and architectural aspect. In chemical way, we want to know the what the polymer chain consists the monomer, what type of monomer, and is there, what type of copolymer is there, what are the parameter related to that, whether this aggregation or three-dimensional structure is there, and how whether the branch chain, the polymer chain is linear or branched or cross-linked, everything we know. If and how they behave with each other, only then we can try to develop a polymer with our appropriate properties. So both these are the two basic parameter, melting point and glass temperature. They play important role determining the ultimate behavior of the polymer. Okay, so we can examine them. See these are the two table where we can again examine the structure of a polymer. See this, the polyethylene, polyester, polycarbonate, polyether, polyamide. These are the different type of the polymer. See, these are the group. Okay, the ester, ether, and oxy. So melting point, it changes like this. For example, M is 2. So here 400, then 395, then 3. Then it increases because the polar group are there. So strong interaction, hydrogen bonding is there. So then it melting point increases. Similarly, here you can see this table. In this table, you see the effect of the aromatic ring. Okay, from 5 to 8. This 5 to 8, aromatic 1, 2, 3. See this glass melting point and glass temperature change here. So effect of aromatic ring in the structure, you can see here. The influence of chain symmetry is also noticeable, even comparing the decomposition temperature of unsymmetrical chain, and this is the decomposition temperature. This is unsymmetrical, this is the symmetrical. The symmetrical one have higher decomposition temperature, they have thermal stability than this is unsymmetrical. So we must know the structure, the monomer, the what kind of chain is there, what are the hindrances is there, whether what kind of forces are possible there. So we can modify the polymer structure accordingly. See here again this figure. This is a nylon 66. If we change this is an important example. If we change the secondary bonding of polyamide in nylon 66, if we change the hydrogen atom with the methylol group in nylon 66, if we change the hydrogen atom methylol group, the loss of hydrogen bonding takes place. And with the increase of this percent of the methylol group, it acts very strong fiber, the same polynylon 66, then it becomes the rubber, balsam, even liquids. So the secondary force is also very important. From nylon 66, whether you want fiber or rubber or these other the viscous type of material, so you have to change, you have to see the secondary forces. So you have to change the chemical composition. So hydrogen atom to be replaced by the another group. So here is this is another picture where we have plotted most of the polymers, the melting point and glass temperature. So this is the range for the linear homopolymer. They behave, all are lie between this. Here the block copolymer, here the random copolymer. So relation between these, it leads to development of the copolymer. The point is if we want to develop a polymer of different desirable property, so we have to prepare the copolymer. Means more than one type of the polymer, one type of the monomer are to be polymerized to form the copolymer, so that we can obtain the desirable TG and desirable melting point. So it leads to the formation of the copolymer. So from here we can have the idea how it changes. So, and most of the polymer now you come across, now come to little bit to the application part. How much more time I can take? Garag Sahab? Hello?
Yes, sir, you are audible.
Yes,
कितना समय और है? Can I take 2-3 minutes more?
yes, you can take.
Sir, you can continue, sir. You can continue, sir.
Okay, okay. So I will be taking just 5 minutes more and I will be finishing it. So, for example, I have given a table here where the most common polymer are listed and their characteristic and their application. So you can have some idea. For example, polyethylene. So it is used in like it is more flexible. So flexible bottle, the toys, tumbler, battery parts, ice tray, wrapping materials. These are it is used. The polyethylene is used for this. Polypropylene, okay, it is some hard than that, so it resists the distortion. It has the excellent electrical property and fatigue strength and chemical inert. It is inexpensive, poor resistance to, although poor resistance to UV. So all sterilizable bottles which have to sterilize, we have to heat roughly to handle. Then polypropylene is taken. So packaging film, TV cabinets and luggage, the rough one, the hard one, for using the polypropylene. The polystyrene, so this is the excellent electrical property and optical clarity. Okay, it has more clarity. It is so good thermal and dimension stability than these two. So the wall tile and battery cases and the good toy lightning panel and the housing plans of the housings made of the polystyrene. The PET, this is another costly and important material. So we have in India, the PET is produced. I will have a table I can show which polymer, the amount of polymer is produced in India. If we have time, I can show that. So this is the toughest one, and this is the transparent one. The good bottles, the ore carbonated bottle, they are made up of the PET, and the fiber, the terylene, are made up of this PET. Okay, so magnetic recording tapes, clothing, automotive tire cords, these all are made from the PET, because the permeability of the gases and other solvent is also less in the PET. They cannot permeate through that, so we can keep for the long period. So that's the important of it. Nylons, we call them the engineering plastics. They have so many strength. They have medical application also, and they are very tough. They have low frictional coefficient. So they are like the silk. So the bearing and the gears and bush and handles and jackets of wires and cables, which are less uh, frictional coefficient and very high strength. So nylons are used, ropes and all made of the nylons. Then the polycarbonates. The polycarbonates, it has dimension stability. It has low water absorption. It is more transparent, so it has good impact resistance. So our helmet, safety helmets, the lenses light glow, the base of photographic films, they are made from the polycarbonates. Polymethyl methacrylate, it has the outstanding light transmission. And for example, our window glass, the glasses of the car here, polymethyl methacrylate is used, and the aircraft glasses and where transparency is required. So the outdoor signs, polymethyl methacrylate is used. In thermostatic polymers, the two important, the epoxy and phenolics. You take the epoxy, so electrical molding, all the zinc and tub, adhesive, coating, and fiberglass laminates. So generally they are reinforced with the glass fiber also. Okay, so they are very tough dimensional stability. Phenolics are used in telephones. These are the colored one, and the electrical fixtures and bakelites and phenolformaldehyde. You know the bakelite, so they have also excellent property. Melamine formaldehyde. So there was one time when the all utensils were of melamine formaldehyde, the white one, and this is the the brown and black one, the phenolics. So many use the adhesives of the epoxies, araldite. So they have the many applications. So always there should be innovation, and that's why we have the new application. So plastic material growth depend upon the innovation, and if they have the application, only then they have the growth. So we have many innovation in area of the plastic, such as the transport and defense, in aerospace, in medical, in the healthcare, and electronics. So polymer electronics is one of such area which has opened up new avenues for plastics, organic light emitting diodes, electro-optical, bioelectrical components, low-cost plastic chips to flexible solar cells. These are the new area, and new plastics conduct electricity, polyesterenes. These are the conducting polymers. They conduct the electricity, so they emit the light. Okay, so although we cannot replace the semiconductor, silicon type semiconductor, but we can approach towards that. So radio frequency identification tags. Okay, so identification nowadays they are used all are of the plastics. So any control of access, payment, tickets, price tabs, everything. And now the medical applications of the polymers is very important. So as I have said earlier, that nowadays we are not talking about the polymer waste. They are useless. They are spoiled as, and although that depends upon the waste management. So how useful even a simple layman, illiterate person can understand how they have helped in COVID-19 today's situation. All the protective equipments are made up of the polymers, whether it is a glove, for example, glove, these are the nitrile and made up of nitrile rubber, natural rubber, polychloroprene. Okay, they are also made up of the non-woven polypropylene fiber, surgical mask, the polypropylene fiber, face shield, made up of polycarbonate, PET, polyvinyl chloride, ठीक है, gown made up of polyester fiber, polypropylene fiber, overall overalls and which are used externally for the body, they are hard, high density polyethylene, non-woven fabrics are used. So they are highly useful nowadays for healthcare worker. Without these, it was difficult to handle the situation today. They have other important applications where we must be very careful about the use of polymer in medical applications. Okay, so generally, roughly we divide into two groups these biomedical applications, that the sufficiently biostable, they must be sufficiently biostable to allow their long-term use in artificial organs, and and biodegradable material that will serve short-term purpose and decompose to small molecules, and they are escaped out the body, and some water soluble or the were used as a membrane for dialysis. So we can classify all the medical applications of the polymers. In polymers for heart pumps and cardiopulmonary bypass surgery, the artificial heart pumps. Okay, the silicone rubber is used, polyethylene rubber, Dacron, polyester, Teflon. These are used. They have so many applications. Okay, and heart valves, polytetrafluoroethylene, prosthesis, prosthesis, artificial limb जो हैं, they are made up of the PET fiber, polytetrafluoroethylene foam, porous polyethylene foam, silicone rubber. So they are used there as the medical application. And the bone joints and teeth, okay, elbow joints, knee joints, the cell phones and silicone rubbers, elbow joints, vinyl polymers, okay, ligaments, Teflon fabric, silicone rubber. So they are used there are contact lenses, polymethyl methacrylate is used, hard contact lenses, soft contact lenses, where we use the hydrogels, okay, and there are many other surgical applications. So most important also nowadays, people are working, scientists are working in drug delivery. That is a important area where the drugs delivery carrier based on natural and synthetic polymer, है ना? So they take the advantage of the mechanism which is used by the pathogen and other cells, है ना, for the selective target. So although I am not a person for medical background, so I tried my best to explain the structure property relations and their importance of development of the copolymers. And once again, I thank you, the principal, Dr. Vikramjit Singh, and Dr. Garg, and other organizing members for giving me opportunity, okay, to have the interaction with the colleague and the scholars and the students. So thank you. If anybody have any questions, please. Garg sir? Hello? Garg sir?
Yes, yes.
गर्ग साहब क्वेश्चन के लिए डॉक्टर साहब क्वेश्चन के लिए बोल रहे हैं.
Yes, sir. Yes, sir. Thank you very much, Dr. Daya, for sharing your finding on polymers. Sir, you explained the importance and the increasing demand of polymers in our daily life in detail. The increasing demand of polymers make them very useful.
स्क्रीन बंद करने के लिए बोलो. स्क्रीन बंद कर दो. आपने शेयरिंग स्क्रीन बंद कर दिया है. भैया कैसे स्क्रीन बंद कर दो.
Daya sir, आप screen
हाँ,
बंद
डॉक्टर
कर
साहब.
दीजिए.
Yes,
बंद
yes.
कर दीजिए, हाँ.
स्क्रीन बंद नहीं है. लेट मी सी. अब बंद हो गया डॉक्टर साहब?
Yes, ये होगा sir. Sir, the increasing demand of polymers and make them more useful. Fundamental knowledge of structure property relation is needed. You mentioned in your lecture. Sir, you also explained that by modifying internal physical and chemical properties, the durability of the polymers can be enhanced. Sir, you told us that flexibility, symmetry, stability, or reflecting their physical properties. Most important point you shared with us, sir, the plastic material growth are widely used in automobile parts, transport, electronics, electrical, defense, and aerospace. Sir, use of polymer in medical applications is still challenge. You pointed out. Sir, there are some questions and queries from our participants. Is it possible to share with you?
Yeah. I will try to answer.
Okay, sir. First question is polymer used in contact lens have some harmful effects? Sir, my question is,
Yes.
is
I
polymer
understand.
used in contact lens
Yes.
have some harmful effects?
Yes, certainly. This is the actually they always there are some effects, and the hydrogels are used as a contact lens. So this is the I already told I'm not from medical ground, but certainly there would be, so precautions will be taken, and the expert that can also explain about that. But certainly there will be some effects, but they are used they are in practice because we have the less harmful effects of those. And I think if we use the contact lenses for the up to the long period, so we have to cap the wet, and if the wetness is not there and hardness is there, that the itching and other many things may happen. So there are some precautions with comes along with the use of the products with many precautions. So we must maintain that. If wetness is there and if we measure all the precautions, then we can reduce to the great extent the harmness of those use of the contact lenses, etc.
The second question from our participant is that what are transdermal drugs delivery system? What are transdermal drugs delivery system?
I'm
Have you some
sorry for
idea
that
about this?
because I'm told that I'm not too much acquainted. I'm not expert on some medical aspects,
Yeah.
and I'm a non-medical, I think, a student. So I have not be able to explain.
Again,
So
sir, same
I'm sorry
third
for that.
question. Yeah. Again, same question is coming. That is biomedical use of polymer is safe. I think this is also same to first question. Is biomedical use of polymer is safe?
Yes, yes, because everything comes. There are precautions. So there are
Yeah.
clinical trials. There are all precautions. If we take all precautions, they are all are safe. And if anything is urgently required and that is that is replaceable and used and make the facilitate our work and human body, so with precaution we should use, and with precautions we can reduce again on the hazardous effects. And,
Sir, is
that
one question is more there. How we can relate polarity with TZ?
how we can relate.
Polarity with TZ.
Okay, TG,
Glass
glass and
glass
temperature.
glass temperature. Yeah.
Okay, polarity with glass temperature. Okay. Actually, polarity, if the change and polymer are more polar, so secondary forces are there, attractions are there. So close packing is there, so that becomes stabilized. So we have to give more. So motions are freezed. So we have to give more heat. So glass temperature is increased in that case. If polarity is more, TG will be increased because of the polar strong attractions.
Thank you, sir. Sir, I think you mentioned in your lecture that polymers are produced chemically. Are they good for human in this pandemic?
Polymers are produced. Please repeat.
Produced chemically.
Yes.
Are they good for human in their pandemic?
Yes, yes.
Yes,
Externally, there is no problem because the monomer, the chemicals, they are polymer. They are get connected. They are bonded in a form of a polymer, which are most of the polymer which are not soluble. So they don't harm. If we use the plasticizer in those, doesn't escape. So they are prepared in such a way that their use doesn't affect our skin in external use at the environment appropriate environment condition at low temperature. There is no effect of that. They are safe.
Okay, okay, sir. Thank you very much. Thank you very much. Now I request Dr. Archana Malik to thank everybody who is directly or indirectly part of this webinar. Dr. Archana Malik.
Good afternoon. I have been given this responsibility to propose the vote of thanks for this wonderful event organized by Department of Chemistry, Dayanand College, Hisar. I know that no words from me can actually be adequate to thank everyone for making this webinar a huge success. Nevertheless, my first thanks goes to Professor Dr. J.B. Daya, Dean, Faculty of Physical Science and Technology, GJU Hisar, who has accepted our request on a short notice to be a resource person of this webinar and spared valuable time from his busy schedule. Thank you, Dr. Daya. My heartfelt thanks to our worthy principal, Dr. Vikramji. Without his guidance, this event could not have been possible. Thank you, sir. I also thank Professor ML Garg convener of this webinar, for putting hard efforts and dedication to make this webinar a grand success. Thanks are also due to the coordinator, Dr. Sunita Lega, and members of the organizing committee, Ms. Anu and Ms. Sikha, for their hard work in making the event successful. My special thanks to faculty of Computer Department for organizing the required setup to host this webinar. Thank you, Professor Narendra Kumar and your team, sir. From core of my heart, I thank to all the participants from different parts of country. Without them, our efforts would not have been so colorful. And in the end, a very big thanks to my dear students who work very hard to make this webinar a huge success. Thank you all and have a good day.
Have a nice day. Thank you very much. Thank you.
Thank you very much. Thank you very much to all. Thank you.
Thank you, Dr. Saab. Thank you to all.
Thank you,
Thank you
Dr.
to all participants.
Thank you, sir. Very, very special thanks for arranging a nice presentation by Dr.
Thank you, sir.
Thank you all. Thank you. I think now I can exit, I think.
Yes, sir.
Yeah,
Yes. Thank you, Dr. Saab. Thank you, Dr. Vikramjit.
Thank you.
have a nice day, sir. Have a nice day.